Topic of today's video will be power series solution of a differential equation. And before actually starting how a solution of a differential equation with the help of power series is obtained, I will start with some basic concepts about power series, right? So an infinite series of the form a0 plus a1x plus a2x square and so on is called power series of function fx about the origin, right? And more generally, I can replace this by we can write this by summation a n x to the power n and starts from 0 to infinity, right? You can write this series in a closed form, summation form. And in general, if I write this infinite series in ascending powers of x minus x naught, a2 x minus x naught whole square and so on, right, is a power series of function fx about the point x equal to x naught, right? The previous series is centered at origin, and the second one is centered at x equal to x naught, right? So you can write few examples of this. Example, you have series of sin x. You know that the sin x series can be written in this form, all odd powers. This is called Maclaurin series also. You must have studied this series in last semester, where you obtained these terms by using the Taylor's coefficients, right? And another example is e to the power x, in which we have all powers of x. So these are two examples of power series, right? Okay, where fx is this function and this is the power series, right? And in this series, some of the coefficients are 0, odd powers of x are absent, while in this series all powers of x are present, right? So we will be taking this concept to solve a differential equation, right? Before that, I will define analytic function and real analytic function, right? So real analytic function, and how a real analytic function is related to this power series, right? So the definition is like this: a function fx, this is a real function, x is a real variable, is said to be analytic on open set. I will write open set D. This is an open set on open set D, which is a subset of real line, right? If for any point x naught belonging to this domain D, fx can be represented by power series representation in x minus x naught to the power n equal to 0 to n. What does it mean by a real analytic function? If you are talking about a real function, definitely the domain of the function should be a real interval, right? So this D should be considered as an open interval, right? You can consider the interval from 0 to 1, open set, right? And this is a subset of real line R, right? And you have any point belonging to that interval, right? And then if fx can be represented with this power series centered at that point, then we say that the function is analytic, right? For example, you have this e to the power x, this function, right? So e to the power x is defined for the whole real line, whole R, right? And you should take any point of that real line. Suppose that point is x equal to 0, and you can write that exponential function in terms of ascending powers of x minus 0. You can see that the series is obtained in ascending powers of x minus 0, right? So we can say that this e to the power x is analytic, right? And again, e to the power series of e to the power x can also be obtained in powers of x minus 1 also, right? This terms will be different obviously, and x equal to 1 belongs to the domain of this e to the power x, right? Similarly, sin x has been represented here in ascending powers of x minus 0. You can see that, and we can also obtain a series in ascending powers of x minus 1 or x minus 2 or any number, because the domain of sin x is the whole real line. It is defined by the whole real line, right? So this is the idea about the definition of a real analytic function. It means that the existence of this power series for that function fx guarantees that the real function is analytic, right? And this power series is valid for some region. It is not like that these series sin x and e to the power x which are valid for over the whole real line. Some functions are, suppose you have function 1 over 1 minus x, 1 divided by 1 minus x, and you expand it with the help of a geometric series using that binomial expansion. You get the expansion 1 plus x square plus so on, and this series is valid for the interval mod x less than 1, right? In that case, the interval of convergence is mod x less than 1, and this is different from these two examples. Its interval of convergence is the whole real line sin x and e to the power x, while the interval of convergence of the function 1 over 1 minus x is only mod x less than 1, right? Okay, so I will be taking this theory further from power series. This is the power series ascending powers of x, you can see that, or ascending powers of x minus x naught. This is called the center of the power series, right? And this is called real analytic function. A real analytic function is defined with the help of this power series. A function having this power series representation is called analytic. So I can say that sin x is analytic, I can say that e to the power x is analytic, and e to the power minus x is also analytic because we have a nice series expansion of it. And all the polynomials are analytic also. Suppose you have polynomial x square plus x plus 1, right? And you can, it is already expressed in this form, 1 plus x square, ascending powers of x, right? So all polynomials are analytic. So you should remember that all polynomials are analytic, sin x, cos x are analytic functions, and exponential functions are analytic functions, right? And there may be more examples of analytic function. 1 over x. 1 over x is not analytic at x is equal to 0. However, it is analytic for all the real line except x is equal to 0, right? It means that where the denominator vanish for a rational function, or you can say for a function of type px over qx, where the denominator goes to 0, the function is not analytic at that point. The key idea is that. Okay, so now I will write the procedure of obtaining the solution of a differential equation, right? So I will consider a second order differential equation, because you are familiar with the second order differential equation. So I will be considering a second order homogeneous differential equation. The right hand side is taken as 0. Homogeneous differential equation like this: y double dash plus px y dash plus qx y equal to 0, right? Where these px and qx are functions of x, px and qx are functions of x, right? And the right hand side is 0. That's why we are calling it a homogeneous differential equation. Okay, and there is a second order differential equation, because you can see that the highest derivative is the second order derivative, right? And in our last semester, we already solved this equation with the help of elementary functions. Elementary functions are like sin x, cos x, e to the power x. They are called elementary functions. When these coefficients were constants, suppose this is a constant, this is a constant, you have a nice method to solve this differential equation by writing its auxiliary equation in terms of m. Then you get roots, maybe distinct roots or equal roots or complex roots. Then you write the solution of this differential equation, right? And in all cases, the solution was of the form c1 e to the power m1x plus c2 e to the power m2x. Or when you get repeated roots, again the exponential function is present in the solution. And when you get the complex roots, then you have exponential function multiplied with the trigonometric functions cos x and sin x in the solution, right? All of that thing you have done in your last semester. But what happens when these px and qx are not constants, right? Then this power series solution comes into play, right? You cannot always solve this type of differential equation when you have these px and qx are functions of x, right? You have to apply this method, power series solution, right? And the good thing about this differential equation is that this is a very important point. If these px and qx are analytic functions, then the solution of this differential equation is also analytic, right? What does it mean? That analytic can be roughly taken as nice behaving function or well behaved functions. We say a function is analytic, it means that the function is well behaved at that point, right? So I will repeat that point. If px and qx are analytic, or I can say well behaved functions at some point x equal to x naught, then its solution, that will be yx, will be also analytic or well behaved at that point, right? So this is the whole idea, this is a central idea to use this power series solution, right? I will write that point. If px and qx are analytic, or I should say well behaved, at some point x equal to x naught, then the solution of this equation number A, yx is analytic, right? So this is the key idea to use this power series solution method. And what we assume that if this condition holds, means px and qx are analytic functions, right? They can be polynomial x square, right? They can be exponential function, sine function. They should be well behaved. They should not have any singularity at x equal to x naught, right? Then we will say that px and qx are analytic functions, and we will hope that the solution is also analytic, and we'll take this yx is equal to this much, and we'll plug this yx in this form here in my differential equation, right? And then I will equate the both sides to get the values of these constants a naught, a1, a2, and so on, right? So I will write that procedure in short, is analytic. So we hope that our solution, that is yx, right? Our solution is yx. We know that the solution of differential equation is y, right? Is of this form, n equal to 0 to infinity and an x to the power n. We hope that this is a solution of A, right? So this is an important point. And since we hope that this is a solution of equation number A, we will plug this yx here, here, and here, and then we will equate both sides to get the value of this coefficient an, right? And after getting the value of this coefficient an will be a naught, a1, a2, and a3, so on. We will plug those values here in this solution. That will be a final solution, right? But the central idea is this: we need this condition to be satisfied. Px and qx should be analytic at x equal to x naught, right? Or should I write x minus x naught here, because I'm talking about x minus x naught whole to the power n, right? So I will write a small example of this. For example, you have this equation y double dash plus x y dash plus x square y equal to 0, right? This is a differential equation, has a solution of the form y is equal to summation an x to the power n equal to 0 to infinity about x equal to 0. You can see that this is x to the power n only, so I have taken x naught equal to 0, as the reason is that this px, your px is actually x and qx is x square. You can see that the coefficients of y dash and y are x and x square. They both are polynomial functions, so they are analytic functions. Are analytic at x not equal to 0, right? So to start with this series, we just need these conditions to be satisfied. The px and qx should be analytic functions, and when this is satisfied, then we'll start with this, that series solution or power series solution, right? I will take example, a kind of motivating example to start this power series solution method. I will take the familiar differential equation of second order, and that is example number 1. Find the solution of differential equation y double dash plus y equal to 0 about the point x equal to 0, right? And you will see that this is a second order differential equation with constant coefficient. Here you have px is actually absent, y dash is absent, so qx is actually equal to 1. And you have already solved this equation in your last semester, right, by writing its auxiliary equation that becomes m square plus 1 equal to 0, and then you get m equal to plus minus iota, and then you get, when you get complex roots, then you write the solution in the form of y is equal to e to the power alpha x multiplied by a cos beta x plus b sin beta x, right? So the solution of this differential equation can be easily obtained by the technique you have studied in your last semester, right? But to give a motivation about this method, I will be solving the same equation with this power series solution, right? But to start with this power series solution, I need to check this condition, px and qx should be analytic, right? So I will just pick px and qx solution. Here px is equal to how much? Px is actually absent here, and qx is the coefficient of y, that is equal to 1. And you can see that these are constant functions, or they are polynomial functions. They both are analytic. You know that polynomials are always analytic, are analytic at this point. The point is x equal to 0, right? So I hope that this technique will work, right? I will assume that this is solution of this differential equation. So suppose the solution is of the form, and let it be y is equal to summation n equal to 0 to infinity and an x to the power n, because x naught is equal to 0, you can write this as x naught, right? Your point is 0, so x to the power x minus 0 whole to the power n, right? So this will be your power series solution. Or you can also write this series in expanded form, that is also fine, but I will do a differentiation of this y in this form only. I need, see here, I need y double dash. Y is already here, I need y double dash, so I will differentiate it twice. And you know that a power series can be differentiated term by term infinitely number of times, right? There is another property of this analytic function. An analytic function can be differentiated infinite number of times. That's why we can always differentiate this power series infinite number of times, right? So I will be going to differentiate this twice, right? So that will give me y dash. If I differentiate it once, that will produce summation n equal to, I will leave this point, an is a constant, it becomes n times x to the power n minus 1, right? And here n should start from 1. That's an important point, right? Why it should start from 1? Because if you start from 0, right, and here you write infinity, then plugging n equal to 0 here will produce x to the power minus 1. It means 1 upon x, and you cannot obtain x in the denominator because you are not having x in the denominator in the original series. You can see that the original series is actually, this is actually a naught plus a1x plus a2x square and so on. All the powers of x are positive, so there is no point of getting a negative power of x after differentiating it once or twice, right? You can see that you put n equal to 0 here, you are getting 1 upon x, and there is no hope of getting 1 upon x by differentiating these terms, You will always obtain positive powers of x after differentiating it any number of times. So there is no point to write n equal to 0. So we should start from n equal to 1. And you can verify this fact by actually differentiating this series term by term. If you differentiate this, this will go to 0. This will become a1. This will become twice of a2x, right? So first term will be a1, right? And that indicates that the suffix should start from n equal to 1 only, right? Okay. So be careful at this point. The suffix should be changed accordingly, according to this power, right? Or according to this suffix also sometimes. So I will differentiate it again because I actually need y double dash. Y double dash. So summation. Again I will leave n equal to how much? I will leave that, and this will become n times n minus 1 x to the power n minus 2, right? Now this time n should start from 2 because there is no point putting n equal to 0 and equal to 1 because that will produce a negative power of x, and that is not possible, right? So this is my y double dash and this is my y. I will be going to plug these values here in my differential equation, but before that you should do some modification in order to ease out the calculation, and that is what hence the terms of this differential equation. First I will write my y double dash, right? I am going to modify this y double dash. How? I will actually scale up this series by replacing n by n plus 2, and it will become summation a n plus 2 n plus 2, and this will become I think n plus 1 and x to the power n, right? Actually I needed x to the power n everywhere, right? In order to do comparison, I need x to the power n term in all terms. That is my goal in all of the numericals, right? And this is also fine. Y is also given in x to the power n. That is also fine, and we do not actually need any modification here. So both terms are in x to the power n, right? And you can write here. Now you can write n equal to 0 because this time n equal to 0 is allowed, right? Putting n equal to 0 here will produce a constant term, that is fine, and infinity, right? So this step is also important. You should note this step. This is just to ease out the calculations, right? And now I will plug these values in my differential equation, right? So plugging these derivatives, these are derivatives and y in the differential equation, that is y double dash plus y equal to 0, right? That will produce summation a n plus 2 times n plus 2 times n plus 1 x to the power n, and here n equal to 0 to infinity, and the second term is plus summation n equal to 0 to infinity and a n x to the power n equal to 0, right? Okay, now what I will do, I will just equate the like terms of both the sides, right? You can see that if you put n equal to 0 in here, you will get a constant term. X to the power 0 will produce a constant here, right? And similarly here. So first I will equate the constants and then the higher powers of x, right? Okay, so I will equate the constants here only, equating constants term both sides, constant terms on both sides, right? So be careful at this point. You should check that whether you are obtaining a constant term from each and every term. First I will check this term, whether I am obtaining the constant term from this. Yeah, if I put n equal to 0 here, this will become 1. So I hope that I will get a constant term, and that will become, putting n equal to 0 here will produce a2, and this will become 0 plus 2, 0 plus 1, that will ultimately become 2, right? Times 2. And from here I will obtain, yeah, putting n equal to 0, I will obtain a naught plus a naught equal to 0, right? So from here I can always obtain a2 is equal to minus times a naught over 2, and this was actually 0 plus 2 into 0 plus 1, that was actually 2 into 1. So should we write it as 2 into 1 in order to generalize it, right? 2 into 1, or minus a naught over 2 factorial, right? And you should always obtain a bigger coefficient. Why I am calling it bigger? Because the suffix is bigger. In these coefficients the suffix is 2, here the suffix is 0, so the bigger coefficient is a2. You should always obtain a coefficient with bigger subscript in terms of a coefficient with a smaller subscript, right? A2 in terms of A0, not A0 in terms of A2. Now I will equate the coefficients of x to the power n directly, right? I have to rub that first. So equate coefficients of x to the power n, right? And from the first term, you can see that from the first term, the coefficient of x to the power n will be a n plus 2, n plus 2, n plus 1 plus a n equal to 0, right? And from here, I should obtain a coefficient with bigger subscript in terms of the coefficient with smaller subscript, right? So that will be like this, okay? And let me call it equation number 1, okay, right? Now, what I will do, I have obtained A2, right? So I should obtain A3 from here, put n equal to 1, I think, yeah. Put n equal to 1. If I put n equal to 1 here, I will get A3 equal to minus A1 over, I should put n equal to 1 here, that will be 3 into 2, and yeah, minus A1 over 3 factorial, if I am not wrong, right? And put n equal to 2 in this, I will get A4 is equal to minus A2 over 4 times 3, right? And A2 is already obtained there, you should use that value. A2 is actually how much? Minus, so that will become plus, I think, plus A0 over 4 times 3, and that was actually 2 factorial. So ultimately that will become A0 over 4 factorial, right? Okay. Now you can see the pattern, right? The A3 was equal to minus of A1 by 3 factorial, A4 was equal to A0 over 4 factorial, so on. I will write few more terms. Put n equal to 3, that will give A5 is equal to here minus of A3 over 5 multiplied by 4, and you can use the value of A3 from here, and that will become, I think, plus yeah, plus A1 over 5 factorial ultimately, right? And then put n equal to 4, that will become A6 is equal to minus A4 over 6 times 5, yeah. And plugging the value of A4 from here, A4 is positive, so that will become negative of A0, 6, 5 into 4 factorial, that will become 6 factorial, right? Now I think we can put these values in our series, right? Putting the values of, I think we got A2, then A3, then A4, A5, A6 in our series, and that was, yeah, that was our series. I will name that equation number something A. Let it be equation number A, right? In equation A, okay, then we will get y is equal to, I will put these values in expanded form. The first is A0 is A0 plus A1x, right? Then A2x square. What is my A2? A2 is actually minus of A0 over 2 factorial x square. Then A3, what is my A3? This is my A3, minus of A1 over 3 factorial x cube. Then A4 is A0 over 4 factorial x to the power 4. Then A5 is again plus A1 over 5 factorial x to the power 5, and then A6 minus A0 over 6 factorial x to the power 6, and so on, right? You can see that all of the terms are containing either the coefficient A0 or A1, right? And that indicates that since only two arbitrary constants are present, it indicates that this is a solution of a second order differential equation, and that fact is already true. You know that this is a second order differential equation, so we should have two arbitrary constants in our general solution, and you can see that this is true, right? And you can take A0 common from these terms, right? So you can write it as A0 1 minus x square over 2 factorial, and then 1 over x to the power 4 over 4 factorial minus x to the power 6 over 6 factorial, and so on. And you can always take common these a's, right? You can write a1 common, and inside bracket will be having x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus so on, right? So this is a solution containing two arbitrary constants. But here you can see that with this arbitrary constant you are getting an infinite series, and this is also an infinite series. And you can recognize these series. These series are very famous series. This is a series of cos. You can write this as a naught cos x. You know that this series for cos x, and this is for sin x. So your solution is this: a naught cos x plus a1 sin x. And indeed, if you try to solve that differential equation with the help of writing auxiliary equation, as you studied in your last semester, you will again get the same solution, right? But the process will be short. This series solution process is long as compared to that elementary method solution, but the solution is same. You can see that, right? Is solution. And at this point, it is not always possible to write this whole series in terms of a closed function, right? It is not like that every time, but somehow we will reach this point. It means that we will somehow solve the differential equation. No matter we can write that series in form of a closed function or not, but we can always obtain a solution of a differential equation with this power series solution, right? And which was not possible with those elementary methods you studied in your last semester, right? Okay, so I will take another example in which this writing this series in closed form is not possible, right? Example number 2, solve y double dash plus xy equal to 0, this equation, about x equal to 0, means this is the point about which you need your solution, right? And this equation is also called Airy's equation, right? Okay, so before starting the power series solution, I should first check my coefficients px and qx, because they are essentially important to start the solution. You cannot always start with that power series. First you have to check that condition that your px here it is 0 and your qx is equal to x. They both are analytic. You can see that is constant function, is a polynomial. They both are analytic at x equal to 0, are analytic at x naught equal to 0. So we hope that this is a solution, summation n equal to 0 to infinity, a power series solution centered at 0. So I will write it as this way, right? Okay, and you should write the expanded version also, a naught plus a1x plus a2x square and so on, right? And let me call this equation number a, right? Now what I will do, I will differentiate it twice as I did in last example. I will copy that from there, y double dash, the value of the terms of D differential equation. I'm writing directly the terms. After differentiating it twice, I will get y double dash, this term, right? And then after scaling up, I will reach here, right? So I'm writing these terms y double dash equal to summation n equal to 0 to infinity, and that was an plus 2 n plus 2 n plus 1 x to the power n, right? And y is still same, n equal to 0 to infinity a n x to the power n. So these are your terms, and you will plug those terms here, right? But no, one more thing, here I have this x into y, right? This is not y, this is x multiplied by y. So what should I do? I should multiply this by x. When I multiply this by x, I will get x times of y, and this will increase the power, right? But that will cause me trouble, because I only need the terms containing x to the power n in this summation form. So what I will do, I will scale down this time, right? So I will write it as, or for this term xy equal to, or should I write it here only, equal to, scaling it down will give me summation a n minus 1 x to the power n and now you should start with n equal to 0. You can also start n equal to 0, right? Fine. And yeah, okay, fine, that's fine. So I will plug these values here in my differential equation, right? So plugging in differential equation, right? Given differential equation, that will produce y double dash plus xy. I should add them. That will produce summation n equal to 0 to infinity a n plus 2 times n plus 2 times n plus 1 x to the power n plus summation n equal to 0 to infinity a n minus 1 x to the power n, right? But yeah, one more thing, important point. There is a danger when I wrote this by scaling it down. I forgot one point. I missed one thing that is very important. I cannot put n equal to 0 because putting n equal to 0 here is giving x to the power 1, x to the power 0. That is fine. But putting n equal to 0 in this suffix, you should also consider the sign of suffix. If I put n equal to 0 here, I am getting a minus 1, and there are no terms containing negative suffix. You know that the power series is containing all positive powers of x and all positive suffixes of a, right? Negative suffix is not allowed. So what should I do? I should write 1 here, right? And that is a very important point. Okay, so you can say that the range of this summation should be written taking the consideration of this a as well as this power of x, both, right? Okay, so it should be n equal to 1, right, and equal to 0. Now I think I am correct. Now what I will do, I will equate the constant terms first. Equate constants both sides. Am I obtaining constant from here? Yes, putting n equal to 0 is producing constant, right? So from this term, the constant term will be obtained by putting n equal to 0, right? This is also an important point. It is not like that you will obtain constant from each and every term. No, because you can see that from here you cannot obtain a constant term. In order to obtain a constant term, you should have x to the power 0, but you are not allowed to put n equal to 0, right? So the constant term will be obtained from this term only in this question, right? So putting n equal to 0 here will give me a2, yeah, 2, 1 equal to 0, since you cannot obtain a constant from here, so right inside 0. So from here you immediately have a2 equal to 0, right? So a2 is 0. Okay. Now what I will do, should I equate one more term? I think if I equate the nth term, then okay, right. So equate coefficients of x to the power n. Okay, so if you equate the coefficient of x to the power n, from here you will obtain a n plus 2 times n plus 2 times n plus 1, and from here you will get a n minus 1 equal to 0, and you can take this on the right hand side. You can write it as a n plus 2 is equal to negative of a n minus 1 over n plus 2 n plus 1, and let me call it equation number 1. Right. Now I will see that whether I am able to obtain, if I put n equal to, I cannot put n equal to 0. First thing is that, because putting n equal to 0 here is producing a n minus 1, that is not allowed. So I should start with n equal to 1. In that case I will obtain a3. Okay, right. a3 in terms of, okay, yeah, that will become 0, that is fine. A naught, okay, fine. I think I should perform one more step here, right? Equate coefficients of x only. The least power was x to the power 0, that is a constant term. The another second highest or second least term is x to the power 1, right? I need to equate this also because I am getting 0 here, that's why. So equating coefficient of x, and be careful at this point. If you want to obtain x term from this summation, you should put n equal to 1, and that will give me a3, and this will become 3, this will become 2 x to the power 1, and from here I will obtain x to the power 1 by putting n equal to 1. So that will produce plus a naught equal to 0. Now I can see that I can obtain a3 in terms of a naught 3 factorial, right? So I will put a box on them. Okay, right. Now I will start putting n equal to 1 here, right? Put n equal to 1. Note that you cannot put n equal to 0 here. Putting n equal to 0 is giving you a negative suffix, that is not allowed. So putting n equal to 1 here in equation number 1, that will produce a3 equal to minus a naught over it will become 3 into 2, right? And that will ultimately become a naught over 3 factorial, right? This is a3. And putting n equal to 2 in this equation number 1 will give you a4 equal to minus, if you put n equal to 2, it will become minus of a1, right? a1 over here 4 into 3. Am I right? Yes. But yeah, that cannot be written as in terms of factors, so rather I should write it as 6 because it cannot be generalized. I think 12. Okay, a4. Now I should obtain one more coefficient. Put n equal to 3, that will produce n equal to 3, that will produce a5 equal to, that will produce, putting n equal to 3 here will give you minus of a2 over 3 plus 2, 5 multiplied by 4, right? And again you can use this value of a2 because a2 is obtained. A2 is how much? Is equal to 0. So a5 will become 0, right? So what can I see? I am having a2 equal to 0, right? a5 equal to 0, right? I need to obtain few more coefficients, I think. Put n equal to 4 here, that will produce a6 equal to minus a3 over 4 plus 2, 6 into 5. And the value of a3 is, where is a3? This is a3, that will become plus, right? So plus a naught over 6 is already there, so 6 into 6 for 30 into 6, 180, right? Okay, and putting n equal to 5 will give you, n equal to 5 will give you a7 equal to minus a4 over 7 into 6. Am I right? Right. And the value of a4 is a1 minus of a1, but it will become plus a1 over 12. So 7 multiplied by 6, that is 42 multiplied by 12. Yeah, 12. Where is that? a4. Yeah, 12. So 504. 504. Okay. So I will plug these values in my series A, right? So therefore A gives y is equal to value of a naught. A naught is not known. A1, the value of a1, that is also arbitrary. Now the value of a2 is 0, so the term containing x square will be absent. Now the next term a3 x cube. What is a3? A3 is minus a naught over 6 x cube. Then what is a4? Minus a1 over 12 x to the power 4. Then a5 is 0, means x to the power 5 term will be absent due to this. Then a6, so plus a naught over 180 x to the power 6, then 7 plus a1 over 504 x to the power 7, and so on, right? So we can write this as, by taking common a naught, we will have 1 minus x cubed by 6 plus x to the power 6 over 180, and so on. And then a1 should be taken common from these terms, right? X minus x to the power 4 by 12 plus x to the power 7 by 504, and so on. So this is a solution, right? And this time you cannot write this infinite series in closed form as you were able to do that in your last example, right? These are not familiar series, you cannot write them in closed form. So you have to keep it with you is a solution, right? Okay, taking another example. Maybe I should change the point, because in two examples I have taken the origin right? X naught is equal to 0. This time I will change the this point, right? Another example, example number 3, and I will keep the same equation. Okay, solve y double dash minus y equal to 0 about the point x equal to 1 this time, right? So I have changed the point, and when you change the point, what you should do, you should first check the coefficients. There is 0 and qx is equal to how much? Minus 1. You can see that they both are analytic at x equal to 1 because they both are constant functions, right? There is no problem, they are well behaved functions at any point, right? Okay, so we should expect the solution of this differential equation is of this form, n equal to 0 to infinity, and this time an, since the point is 1 this time, so be careful at this point, x minus 1 to the power n, right? Okay, and differentiating it twice, I will get, I'm differentiating it twice, okay, once and twice. So I will obtain y double dash and summation n equal to, I'm leaving it, that will produce a n into n minus 1 x minus 1 to the power n minus 2, right? And since it is n minus 2, so I cannot start with n equal to 0, I have to start with n equal to 2, right? But I need both of these terms in powers of x minus 1 whole to the power n in terms of nth power only. So I will scale up this term, or I will write it as, I will write it here only, equal to summation, scaling it up by 2, an plus 2 n plus 2 n plus 1 x to the power n, and now I can start with n equal to 0, right? So plugging these values here in my differential equation, plugging in given differential equation will give you summation n equal to 0 to infinity an plus 2 n plus 2 n plus 1 x to the power n minus summation n equal to 0 to infinity an x to the power n equal to 0, right? Okay, so now what I will do, I will, this is x minus 1, yeah, I made a mistake here also, x minus, this is x minus 1, x minus 1 to the power n and minus summation n equal to 0 to infinity a n x minus 1 to the power n equal to 0, right? And first I will equate the constant terms, equate constants on both sides. So from here I will obtain a constant if I put n equal to 0, right? We should check each and every summation that whether we are obtaining a constant or not. From the first summation I am obtaining a constant by putting n equal to 0, so that will produce a 2 2 1, and from here I can obtain a constant by putting n equal to 0, yeah, that's fine. Okay, yeah, that will produce minus a naught equal to 0, and that will give you the value of a2, a naught over 2 factorial, right? And now what I will do, I will equate coefficients of the highest power, that is x to the power n, right? Now first I equated the least power and then the highest power, oh sorry, again x minus 1 to the power n, okay, right? From here I will get a n plus, if I equate x minus 1 to the power n, the coefficient will be this, n plus 2 n plus 1, and from here the coefficient will be minus of a n equal to 0, so that will produce you a n plus 2 will be equal to a n over n plus 2 n plus 1, so this should be equation number 1. And if you put n equal to 0, if I put n equal to 0 here, I will get a 2 equal to a naught over 2 into 1, right? And the value of a naught, okay, that is not known, that will give you a naught over 2 factorial. That is already found. Sorry, we have repeated that step. I should put n equal to 1 in order to get a3, and this will become a1, and this will become 3 multiplied by 2, right? So a1 over 3 factorial, or you can write it as 6 also. Both are correct. Now we will see that what happens if I put n equal to 2. A4 equal to a2 over 4 into 3, right? And a2, yeah, a2 is known. A2 is how much? A naught over 2 factorial, that will become a naught over 4 into 3 into 2 factorial, that will become 4 factorial ultimately. So I am getting some pattern, right? So put n equal to 3. If I put n equal to 3 here, I will get a5 equal to a3 over 5 multiplied by 4, and I can use the value of a3. There is my a3, this is my a3, a1 over 3 factorial, so that will become a1 over 5 into 4 into 3 factorial, that will become 5 factorial, right? So the next terms will be similar. A6 will be, I think, a naught over 6 factorial. A7 will be, I think, a1 over 7 factorial, and so on. So I will plug these values in my solution. This is my equation, that equation number A, I will call that equation number A, right? Substitute these values in your solution. Your solution was of the form summation a n x minus 1 whole to the power n, and you should write your solution in expanded form also. A naught plus a1 x minus 1, a2 x minus 1 whole square, and so on, right? So that will produce y is equal to, the value of a naught is a naught, that is fine, a naught, and you can see that where is that a2, where is my a2, yeah, a2, a4, a6 means all even coefficients, right? They are in terms of a naught. So I will take a naught common from them, so that will give me a naught, first is 1 plus x minus 1 whole square over 2 factorial, right, plus x minus 1 whole 4 over 4 factorial after taking common and simplifying, and so on. And from the odd coefficient, I can always take a1 common, and the first term will be x minus 1 plus x minus 1 whole cube over 3 factorial, and x minus 1 whole to the power 5 over 5 factorial, and so on, right? So this is the solution, and if you notice it closely, then you can see that this is series of cos hyperbolic, yes, and this series of sine hyperbolic, right? They are familiar functions. You can write it as yx is equal to a naught, the series for cos hyperbolic x minus 1, and another one is series of sine hyperbolic x minus 1, right? So this is a solution, and this time we were able to obtain the closed form of those two series, right? Okay, so this is how a power series solution works when the point is not origin, x equal to 1, right? I will take the last example, example number 4, and that is solve x square y double dash, no, it should be 1 plus x square y double dash plus xy dash minus y equal to 0 about x equal to 0, right? Now you can see that in this example, your px and qx should be first obtained by dividing this whole equation by 1 plus x square, right? So far in all the examples, the coefficient of y double dash was 1, and you should retain that fact. The coefficient of y double dash should be strictly 1, because your standard equation is y double dash plus px times y dash plus qxy equal to 0. So you need to divide this equation by 1 plus x square, and after dividing it, you will obtain your px will be x over 1 plus x square, and qx will be minus 1 over 1 plus x square, right? And now you have to verify that whether these are analytic functions at x equal to 0 or not. First thing is that they are not polynomial functions, as we have seen in last 3 examples. They are not sine or cos functions, they are not exponential functions, right, where you can say that they are always analytic. No, you should check that at this point x equal to 0, whether x equal to 0 is a singularity of this function. By singularity I mean that whether the denominator is going to 0 or not at this point, You can see that if you put x equal to 0, the denominator is 1, that is a good thing, and the numerator is 0, so you will get 0. And here again you will get -1. So everything is fine with this point. It means that x equal to 0 is not a singular point of this thing, this px and qx. So we can say that this px and qx are analytic at this point, right? Are analytic at x equal to 0, right? And one more thing, merely checking that px and qx exist at some point, you cannot immediately declare that the function is analytic at that point, right? Analyticity is something different, right? If you differentiate this px and qx infinite number of times and you go on plugging this x equal to 0 in each of its derivatives, then all of those derivatives will exist, means they will not blow to infinity, right? Not only the function px and qx exist at x is equal to 0, but also their derivatives of any order are existing at this point. This is another important point. You cannot say that if a function is, suppose you have px is equal to mod of x is existing at x is equal to 0. If you put x equal to 0, you are getting mod 0 equal to 0. But you cannot say that it is analytic at x equal to 0, right? Because it should be differentiable at x equal to 0 infinite number of times, right? So be careful at this point, right? Okay. So this px and qx, they are analytic. So we hope that our solution is of this form, summation n equal to 0 to infinity and an x to the power n, because the point is origin this time, right? So what I will do, I will differentiate it once and twice also. Differentiating it once, I will have n equal to 1 to infinity n times x to the power n minus 1, right? And since I have got x to the power n minus 1, that's why I have started with n equal to 1. If you start with n equal to 0, that will produce a negative power of x, and that is not possible. And y double dash summation n equal to 2 to infinity n times n minus 1 x to the power n minus 2, right? But this time the terms of this differential equation should be taken one by one. The first term, if you multiply this by 1, you will get to y double dash, right? So I will write y double dash. And remember one thing, I need all terms containing x to the power n, right? And in this case I am having 4 terms. First term, second term, third term, fourth term. So all 4 terms should be written in such a way that x to the power n should be visible in all the summations, right? So y double dash, but this is x to the power n minus 2. So should I scale it up? Yes, I should scale it up. On scaling it by n plus 2, I will get summation n equal to 0 to infinity an plus 2 n plus 2 n plus 1 x to the power n. That is fine. Now see the second term. Second term is x square times y double dash. Y double dash, yeah. And if I multiply it by x square, then ultimately I will be having x to the power n, right? And then my work will be done. So x square y double dash, and we are multiplying x square with y double dash with this term, not with this. Otherwise that will produce x to the power n plus 2. You should aim at getting x to the power n finally, and I am getting my goal after multiplying this x square by this y double dash, right? So you should multiply x square with this, not with this y double dash. Okay, that will produce summation n times n minus 1 and x to the power n, right? And now I can start with n equal to 0 to infinity. So these are the first 2 terms. Now the third term, that is x times y dash. Yeah. Here's my y dash, this is my y dash. If I multiply it by x, I will get x to the power n, right? So my goal is achieved. n times x to the power n, right? And simultaneously I am working on these range also. You should notice that. Okay, and the last term is y is fine. Summation n equal to 0 to infinity an x to the power n, right? So I will plug these terms in my differential equation, in this equation, right? On plugging in this differential equation, right, and on equating the coefficient, I am writing that directly. First I will equate the constants and equate constant terms, right? You can see it from here. I am not putting all the terms here, right? So you should equate the coefficient from these four terms. From first term I will obtain the constant term, that is a2 2 1, right? From this term I will again obtain the constant, that is by putting n equal to 0, that will produce a naught. 0 times 0 minus 1, that will produce 0, right? So that is 0. From here I will again obtain the constant term plus a naught times 0, that will again go to 0, right? From the fourth term I will get the constant term, that is a naught, and but remember this sign is minus, so minus of a naught equal to 0, and that will produce a2 is equal to a naught over 2 factorial, right? Okay. Oh, what should I do now? Should I equate the highest coefficient of x to the power n? Yeah, from here I will obtain x to the power n, and that is okay, yeah, a n plus 2 times n plus 2 n plus 1, and from here I will get a n times n minus 1. From here I will get a n times n, and from here I will get minus a n equal to 0, right? And I should obtain a coefficient with higher subscript in terms of the coefficient with lower subscript, and I think that will cancel. A n and minus, that will cancel, that will ultimately become a n, and this term will be cancelled, so a n is square, I think 1 minus n square, right, over n plus 2 and n plus 1, if I am not wrong. A and n, that is cancelled, a and n square, right, n square minus 1, and then 1 minus n square, right, that is fine, right? And should I write it as n square minus 1 and put minus here, n square minus 1, okay. So this will be my equation number 1. So put n equal to, if I put n equal to 0 here, I will get a2, but a2 is already obtained, so I should start with n equal to 1. So that will produce a3 equal to minus, and putting n equal to 1 will give you 0. You can see that. So that is producing 0. Okay. Putting n equal to 2 here will produce a4 equal to a2, and 2 square minus 1, that is 3, right? So 3 over, or should I write it as n minus 1, n plus 1, and cancel one of the terms, right? That will be more simplified version of this thing, right? So that will ultimately produce you minus an over n plus 1 and n minus 1, so n minus 1 is, should be n minus 1 over n plus 2. Now it looks fine, right? One term can be cancelled. Okay, so now putting n equal to 2 here, a4, that will become 4 minus 1, 3, yeah, that's fine. a2, that is fine. Okay, and here you will have 4, right? And a2 can be used, the value of a2 is 3a naught over 4 into 2 factorial, that will become 8. No need to write factorial now, right? This is a4. Now put n equal to 3 here, you will get 3. Putting n equal to 3, this is a5, and this will become minus of a3, and this will become 3 minus 1, 2, yeah, 2 over, here you will have 3 plus 2, 5, and the value of a3 is 0, so ultimately it will go to 0, right? So at last I will have n equal to 4, a6 is equal to 6, okay, that will become minus a4, and putting n equal to 4 here will produce 3 over 6, right? And putting the value of a4, what is my a4? This is my a4, that will produce minus, the value of a4 is 3a naught by 8, and this is cancelled with 2 in the denominator, and I think 2 at 16, if I am not wrong, 3a naught, right? This is the value of a6. Now I think I can put these values. I have got a2, right? a3 is 0, a4, a5 is 0, a6. So this is a naught. With a naught I have 3 terms, and a1 is okay, right? So therefore my solution will be y is equal to a naught. What is my a naught? A naught is a naught, right? And you can see that a naught can be taken common from these terms. A naught 1 plus x square by 2 plus, is that a3, a4, 3 by 8 x to the power 4 and so on, and only one more term is there, minus 3 by 16 x to the power 6 so on, and plus a1x. This is the solution, right? Now you can see that only two arbitrary constants are present in the solution, right? And since the original differential equation was of order 2, so that's why only two arbitrary constants are present. And again, this time we are not able to get the closed form of the function in the solution y, right? So the central idea behind this power series solution is that your px and qx should be analytic at the point x equal to x naught, right? And we also say that x equal to x naught is an ordinary point of this differential equation. Whenever you have these p and q are analytic at that point, the point is said to be an ordinary point, right? And now the question comes, what happens when this point is not an ordinary point? It means that when this point is a singular point of this px and qx, singularity means suppose you have px is equal to 1 over x, right? And putting x equal to 0 will blow up this function px, right? You will get 1 over 0 infinity. In that case, you will say that x naught is a singular point of your px and qx. Then this approach doesn't work. Power series solution, we have to do some modification on this power series, and that will be our part of next video, right? That is called Frobenius method, when we do some modification in the power series solution due to the fact that the point is not an ordinary point, rather it is a singular point, right? So I will be discussing that case in the next video. For this video, thanks.